Hi students, in vapor compression refrigeration we have seen different conditions like subcooling, superheating and dry saturation before compression and both superheating and subcooling. So these are the four conditions that we have seen. So in this video, we will solve one numerical based on intercooling or subcooling. Okay, so the question goes like this: a vapor compression refrigeration of 10 tons capacity using Freon 12 as refrigerant has an evaporator temperature of minus 10 degrees Celsius and a condenser temperature of 30 degrees Celsius, assuming simple saturation cycle with an intercooling at 5 degrees Celsius. This is also called as subcooling. Intercooling is also called as subcooling. So we need to find mass flow rate of refrigerant in kg per minute and power input and coefficient of performance, where Cp of vapor is equal to 0.72 kilojoules per kg Kelvin. So for any problem we need to write, first we need to draw the temperature, entropy and pressure enthalpy diagrams. So let us draw temperature, entropy and pressure enthalpy. So temperature, entropy you have to draw like this. So it is intercooling, so it will start from first dry saturation, second point 2, and then come back to dry saturation, and then 3. After reaching 3 there is a subcooling, so this is 3 dash, and then it will come back to 4, and then it will go to the first region. So this is 4. So the same way we need to draw in pH diagram. So it will start from here 1, 2, and then 3 to 3 dash, and then it will come back to 4. It should be straight line, and then this is 4, and then it will come back to the 1 region. So this is the temperature, entropy and pressure enthalpy. So first one is T1 temperature is equal to minus 10 degrees Celsius and T2 is equal to 30 degrees Celsius. So let us take, this is T1 and this is T2. Okay, and so 5 degrees subcooling. So from here to here there is a 5 degrees subcooling. So that means there is one more temperature which is T3, or is condenser temperature. Tc is equal to 30 degrees. So that means so T3 dash. So T3 dash is equal to 25 degrees, because this is 30 minus 5 degrees will become 25 degrees Celsius. So now from data handbook, so this is the compressor, this is the evaporator, and this is the condenser. Evaporator temperature is T1 and then condenser temperature is equal to T2. So T1 is equal to, this is evaporator and this is condenser. So evaporator, if you take minus 10 degrees Celsius from data handbook, so HF is equal to 26.851 and HG is equal to 183.058, SF is equal to 0.1079, SG is equal to 0.7014. So everything will be available from the data handbook at T is equal to minus 10 degrees Celsius. In the same way, T2 is equal to 30 degrees Celsius, HF is equal to 64.539, HG is equal to 199.475, SF is equal to 0.2397, SG is equal to 0.6848. Okay, so first we need to find out all the temperature, all the enthalpies, H1, H2, H3, H3 dash, H4, So then only we can solve the problem. So H1 is equal to Hg, which is at evaporator temperature. So Hg at T1 temperature. H2 is equal to Hg plus Cpg into T2 minus T2 dash. H3 is equal to Hf minus Cpg into, this can be a fluid F, T3 minus T3 dash. So H4 is equal to this H3 dash, H4 is equal to H3 dash. So now we know T1 dash, but we don't know T2, so we need to find out T2. So for that, S1 is equal to S2, because this S1 is equal to S2, entropy 1 is equal to entropy 2. S1 is equal to Sg at T1 temperature is equal to Sg at T2 temperature plus Cpg into ln T2 by T2 dash. So Sg at T1, so this is T1, 0.7014, 0.7014 is equal to, here Sg is equal to 0.6848 plus Cpg, it will be given in the problem, or else we need to take this Sg value as 0.73, ln T2 we don't know, we need to find out, and T2 dash is equal to this 273 plus 30, so it is equal to 303 kelvins. So with this we will find out T2 is equal to 309.96. so with this we will find out the T2 temperatures. So we can find out H1. So H1 is equal to this is Hg, so H1 is equal to Hg 183.058. H2 is equal to Hg of second temperature, which is nothing but 199, so 199.475 plus Cpg 0.73 into T2 minus T2 dash. T2 just now we have found out 309.96 minus T2 dash is equal to 303. So it will become 204.55 kilojoules per kg. Next, H3 dash is equal to H3 second temperature, HF SF is equal to, so SF we need to write, so SF is equal to 64.539, which is nothing but HF plus minus, so 0.94, it is Cp of fluid, so that also this is a constant value which will be there in the data handbook, otherwise it will be given in the problem. So 0.94, this value will be standard, will be given in the problem, or else it will be available in the data handbook, into 30 minus 25, which is nothing but T3 minus T3 dash. T3 is equal to 30 minus T3 dash is equal to 25. So here we can add plus 273 plus 273, otherwise even if you don't add, the value doesn't change. So that's why I am putting the same value, 30 minus 25. So this will become 59.83 kilojoules per kg. So H4 dash will be the same, which is nothing but 59.83 kilojoules per kg. So in this, first we need to find out mass flow rate. M dot R is equal to total heat transfer divided by refrigerating effect. Total heat transfer is equal to 10 tons given, so 3.5 kilo, so 10 into 3.5 divided by refrigerating effect is equal to H1 minus H4. H1 minus H4 is equal to 10 into 3.5 divided by, so H1 is found out 183.058 minus H4 is equal to H4 or H4 dash. It is 59.83. So this value will become 0.284 kg per second. So next one, this is the first one. Second one is power developed. power is equal to m dot r into compressor work. So the same value 284 into H2 minus H1. So that will become 6.10 kilowatts. The last one is COP. COP is equal to refrigerating effect divided by H2 minus H1, which is nothing but compressor work. Here this will become 5.73. Okay, thank you.